Howdy, welcome back to the channel. In this video, we're going to go over beam deflection. We have a cantilever beam subjected to some distributed load and a concentrated moment at the end. All right, so we have a W12 by 26 wide flange I-beam loading as shown below, and it is made out of ASTM 20 gray cast iron. What we want to do is we want to find the maximum deflection and slope at the end of the beam, specifically the left end or this point B over here. We want to figure out this point B up or down, as well as what is the slope of the tip of that beam. So let me move to OneNote so we can go ahead and start working on it.
All right, so here we are in OneNote. I've copied the problem, and since we're working with the method of superposition, the first thing we want to identify is what types of loading are there applied to the beam. And what we can see is that we have a moment at the end, and we have a distributed load that spans about, exactly halfway. Now this problem is a little bit weird in that the support here is at the right-hand side. And that's a little bit weird because when we go look for the solutions in the equation booklet that I have copied here below, for the solutions we have that the support or the fixed connection is going to be at the left hand side, as we can see here, and as we can see for the other solution right there. So here the first thing that I would recommend is go ahead and we can flip or we can mirror the problem horizontally about an axis right there. And so what we would have is a beam that looks something like this. For the case of the moment, our beam would look something like this. And now the support is over here on the left hand side, that it would be point A. Point B would be on this other end. And the moment would look something like this. And now doing the same thing, mirroring, so we can make the solution have this kind of the same form or the same orientation of the pre-solved solution. It would look something like this. Again, we have point A, have point B on the other end, and for this other case, we would have a distributed load that spans about halfway of the beam. Next, what I would want to do right here is go ahead and transfer the dimensions. So the beam has a span of 8 plus 8 or 16 feet, which when multiplied times 12 gives 192 inches. So this is 192 inches that way. And for the distributed load, what is 8 feet? 8 times 12 is 96. So this distance is 96 inches. The end of the distributed load, and from the end of the distributed load to the other end of the beam is another 96 inches. And again, the total dimension would be 192 inches. We might need this, we might not. Might as well and change all the dimensions to inches, so that when we do the plug and chug in the equations, we're not having to change the units inside the upcoming equations. So let's go ahead and also change the units for the moment. The moment is 10 kips, which is 10,000 pounds. So we take 10,000 pounds, and this is on a per foot basis. I'm sorry, on a times foot. So we change 2 inches by dividing by feet. We multiply by 12, and we get that the moment then is 120,000 pounds in inches. Similarly, let's go ahead and convert the distributed load, which is over here, 8,000 pounds per foot. But again, we want to work in units of inches. So in 1 foot, there's 12 inches. So we take 8,000 divided by 12. We get 666.67 pounds per inch. Yeah, so now we have everything in the base units that we can plug in the formulas. What I like to do also at this point is go ahead and draw the elastic curve. And so we can see here, for example, for the case of the bending moment, uh, this is going to create an elastic curve that kind of goes downward like this. So we can see, for example, if we were to track this point B, the new location of point B, which I'll call B prime, is going to be below, right? So that moment is causing a downward deflection at point B. Remember, that's one of the things that we want to keep track of. And well, the angle that the beam makes with the horizontals, this angle theta, would be a clockwise or called a negative angle. I'm gonna put here clockwise. Now, when we draw the deflection curve for the distributed load, it's gonna look like the one here below, except well, it points in the opposite direction. So we start here at the center, more or less, and this guy's gonna curve up like that. So if we keep track of that point, V prime is gonna go, in this case, is gonna go up. And that angle theta over here is going to be a counterclockwise or a positive number. So what those numbers are going to be, let's go ahead and do them. And let's start with the moment, and let's solve for the deflection. So the deflection from the moment. Oops, not this keyboard, sorry about that. Let's do this one right there. So deflection, V equals mx squared by 2i. So yeah, at this point, we're gonna need both the elastic modulus and the moment of inertia. So let's go ahead and go to the equation booklet. We find the elastic modulus and moment of inertia. Here we go. So I'm gonna scroll up. There we go. This table shows the materials properties. We want it in units of inches. And here I highlighted the ASTM 20, the gray cast iron. So it tells us that the modulus of elasticity is 10 times 10 to the 3 KSI. Or we can write this number down and put it here in the middle because I'll need it for both. E as 10 times 10 to the 6 PSI, or pounds per square inch. The other information that we need is the moment of inertia, I. And remember the beam, it's a 12 by 26 beam. Oops, wrong one. So let's go over here and let's scroll down. Oh, I'll press the wrong key. 1 second. Down. There we go, the I beam. And we're looking for a 12 by 26, which I've highlighted over here. And what is the moment of inertia about the neutral axis XX is 204 with the units of inches to the 4th power. So we can write over here 204 inches to the 4th power. All right, so let's go ahead and do the plug and chug. So the moment is 120,000 pound inches. X is a distance where we want to figure out the deflection, which is in this case is the whole, it's going to be the whole length of the beam. So X in this case is 192 inches divided by 2 divided by E, which is 10 times 10 to the 6 pounds per square inch, times I, which is 204 inches to the 4th. Now we plug this in the calculator, we get 1.08424 inches. And again, if we go back to the expected deflection, we expect B to move down, right? So this is a downward deflection. Now let's go ahead and calculate the deflection due to the distributed load. We have two equations. If you notice the limits for the equations, one is for x between 0 and a, where a is the span of the distributed load. And then the second one is for x values between a but less than or equal to L, which is the length of the beam. So that's what we want because we want at the edge, we have to use the second equation. So the equation for the deflection in that case is going to be W, the distributed load, times A cubed divided by 24 EI times 4x minus A. So if we go ahead and put the values, the distributed load is 666.67 pounds per inch times A. A is the span of the distributed load. We can see here it's 96 inches. That gets cubed divided by the constant 24 times E. This over here is EI. Let me fix that equation. EI, where E is 10 times 10 to the 6 pounds per inch squared, and I is 204 inches to the 4th. Now we're not done yet, right? We have to multiply times the quantity in parentheses, which is 4 times x. Again, where x is where we want to calculate the deflection. In this case, the deflection is at the end of the beam. So the x takes a value of 192 inches minus A, where A is the span of the load, or minus 96 inches. All right, so we go ahead and plug in those numbers to the calculator. We get a deflection of 8.09567. I like to include a lot of digits after the decimal point to be more precise. And again, if we go back to the drawing that we made for the elastic curve, we see that the deflection is on a up, right? So this is up. So we can see, right, the two are competing. The moment is trying to deflect the tip of the beam down, where the distributed loads ends up deflecting it up. Note that deflection is bigger, right? This number is bigger. So at the end of the day, the end of the beam is going to deflect up. So how much? Well, that's simple. We just take this number, 8.09567 minus 1.08424 inches. And then what we get from that one is 7.011 inches, right? Since the 8 inches is bigger, right, and that was upward, we can say that the deflection of point B then is 7.011 inches up. So that's one part of the question. If you remember, the other part of the question was that we needed to figure out not just the deflection, but also the slope at the left end of the beam, which is the slope at B over here. So let's go ahead and do that one. We have the equation for the slope. For the case of the moment, the equation is theta equals ml. The keyboard, excuse me. Theta equals ml divided by EI. From over here, let me try to scroll down. There we go. For the moment is 120,000 inches. L is the length of the beam at 192 inches. And we divide by E, which is 10 times 10 to the 6 pounds per square inches. And I is 204 inches to the 4th. Now, when we check the units real quickly, remember when we're doing the theta, pounds cancels with pounds. We have inches to the 4th minus 2, so that gives inches squared at the bottom, which we're going to cancel with these two. And what we end up with is a unitless number. It's a unitless number, which means that the angle is in radians. And here, when we plug it in, that number is 0.01129 radians. And remember, we can take that number and we can convert it to degrees by multiplying times 180 and then dividing by pi. So when we go ahead and do that, we get that the angle is 0.6471 degrees. Now, what is the orientation? Again, from our elastic curve over here, we can see that that angle theta is going to be negative or clockwise, right? So it's a clockwise, it's in that direction, clockwise. Let's go ahead and figure out what is the contribution from the distributed load at the formula for the angle. Oops, sorry. The highlighter is as given as theta equals W times A cubed divided by 6 pi. Right, where the distributed load is 666.67 pounds per inch. A is the span of the distributed load, which is 96 inches. Remember, this number gets cubed, divided by the constant 6, divided by elastic modulus, or 10 times 10 to the 6 pounds per inch squared, for the great cast iron, right? And I is 204 inches to the 4. Now we go ahead and plug that into the calculator. We get 0.04819. That's going to be in radian, right? And if we convert to degrees, we can multiply times 180 degrees divided by pi radians. We cancel the units of the radians. And what we have is 2.761 degrees. Now, there's more than just a number. We have to figure out what is the direction. From our elastic curve that we drew up above, we see that that direction is clockwise. Hold on, that's not clockwise. I messed that one up. This is counterclockwise. See, the angle is that way. That's counterclockwise or a positive. Right, so this is counterclockwise, right? Positive or in that direction. So then what's the slope at the end? Well, you guessed it, right? We have the two numbers. Obviously, this one here is bigger than that one. So when we take the difference as 2.761 minus 0.6471, you get that the angle is then 211 degrees. Again, because the 2.7 is bigger and that was a counterclockwise, we can write here counterclockwise, right, or that direction. So if we draw a quick sketch, right, from what we have here, if I have the beam, right, here is point A, here's the end, it's point B. We see that the deflection was upward, 7.011 inches. Right, so it's going to do something like at the very end, right, it's going to move up a total of 7.011 inches. And that angle, theta, is 2.11 degrees, right? It's going to be counterclockwise or in that direction, counterclockwise. Now, if you remember, this is not what the original problem looked like. We had mirrored, right? But it doesn't mean that that's not the answer, right? We can go ahead and imagine that we mirror about a line right here. And now the beam, oops, let me change the color. Here's the original beam now supported over here. Now we know that this point here is going to move up, right, by the same angle. About 7 inches up. And with an angle now of 2.11, except keyboard. Now the angle is in the other direction, which would make it a clockwise direction. Right? So the distance in inches doesn't change. 7.011 inches up, right? But what changes is going to be the angle, and that's because we have to mirror the problem to go back to the original. So there we go. That's the answer for that one. So thank you for sticking around to the end of the video. If you have any questions, please leave a comment down below, and I'll try to get to you as soon as possible. Also, if you found the video helpful, I appreciate if you give it a thumbs up. And if I don't see you in class, I'll see you in the next video.